All right. In the first video, I talked about the radiation emitted by black bodies and went through the argument that caused Planck to propose that the vibrations of atoms in solids occurred at quantized frequencies or with quantized energies, right? That there were certain vibrational frequencies that were possible and others were not. And that's a strange idea, but that's the beginning or the sort of birth of the ideas of quantum mechanics. In this video, we're going to talk about a related subject, which is the heat capacity of a solid, and particularly the way it changes with temperature. So first, a quick reminder of what exactly the heat capacity is, right? We're going to talk about heat capacities at constant volume. Because we're talking about solids, the heat capacity at constant volume and at constant pressure would be very much the same thing. There would not be substantial differences between those, although that's different for gases. The heat capacity just tells us that the change in internal energy is that heat capacity times the change in temperature, right? That's just a nice, simple definition of what we mean when we say it's the heat capacity. If we wanted to measure that C sub V, where again the sub V is for the constant volume piece, we could measure that by doing calorimetry, right? If we knew the energy input to an object and we could measure how much its temperature rose, we could use those things to find the heat capacity. Alternatively, if we have an equation for the internal energy, then the heat capacity would just be the temperature derivative of that particular expression, right? So as it says on the bottom there, if I know the expression for U, the internal energy, then I could use that to say that this du dt is going to give me the heat capacity. The subscript V over there again is just that we would be taking that derivative at constant volume if that actually appeared, if there were volumes in the expression, which in our case there are not going to be, but that just keeps us kind of reminded that that's what we mean when we say C sub V. So the origin of the heat capacity of solids, or the mechanism by which solids can take up energy, is again got to do with vibrational motion of the atoms or molecules making up that solid. Okay, just like in the case of the black body emission, we said the origin of the radiation was that there were vibrations of the atoms in the solid, those so-called oscillators, and that would be the source of radiation. The same is going to be true for where the energy goes if we are heating up a solid, right? So the simplest one to visualize is to imagine something that is in a simple cubic lattice. That just means that each atom in my solid would have 6 nearest neighbors, okay? And so there turn out to not be very many things that crystallize in simple cubic lattices, but the same arguments work in other crystal structures. It's just simpler in the case where all the directions are symmetric. So that says each atom has 6 nearest neighbors, and we're going to picture each atom as being joined to those 6 nearest neighbors by a collection of springs, okay? Just like in the little picture over there. And so it labels these as ideal springs. That just says they're going to follow Hooke's law, right? They're going to the atoms are going to oscillate harmonically, and if we were doing the full development of all the modeling here, that would help us to drive some of the equations. We're actually just going to grab some results, but that's how we would get to that argument. Okay. Each atom will contribute 3 possible vibrations or vibrational modes. Again, where that mode word just refers to a channel that we could deposit energy in, right? In this case, those 3 modes per atom can be thought of corresponding to moving that atom, say, in the X, Y, or Z directions, right? I've got a 3-dimensional solid, and that says any given atom can move in any of the 3 directions in order to, as it takes up energy. Okay, so that's going to help us later on count up the number of possible vibrations that we would have in a hunk of solid. So if we go back into the 19th century, relatively early in the 19th century, back to 1820, there are experiments that are done that measure the heat capacities of various solids, mostly metals, around room temperature. Okay, around room temperature, because doing experiments at extreme temperatures in 1820 was less simple than it is now. Okay. And those experiments generally suggest that the heat capacity of most solids around room temperature is very close to 3R, where R is the gas constant, right? That gas constant in joules is 8.314 joules per Kelvin per mole. So multiply that by 3 and you get 24.9 joules per Kelvin per mole. So roughly 25 for that heat capacity. And that seems to apply to lots of different solids, all right? There actually turns out to be a way to rationalize that value of 3R by using arguments about what is known as the equipartition of energy. And we'll meet up with that idea in more detail later when we talk about vibrations and rotations of molecules in chapter 5 of your textbook, I think. But for now, we'll just say that that 3R value makes sense in a classical picture of things, okay? Exceptions to that are mainly seen for very light elements and or solids that have very high melting points. In many cases, those turn out to be the same set of things. But in those cases, there are some pretty strong deviations from those values, from that expected value of roughly 25 joules per Kelvin per mole. Okay, but overall, the model works. This comes to be known as the law of Dulong and Pettit, that just says you can take a ballpark guess and say that would be the heat capacity of a solid. Turns out later on, people begin to be able to do experiments at lower temperatures. And this is just sort of the evolution of available technologies in research and in labs. It becomes possible to get liquid nitrogen relatively easily. Okay, before there's liquid nitrogen available, getting something cooled down to 100 Kelvin, for example, is a very, very difficult challenge, right? Liquid nitrogen, which if we were on campus, there's around campus a whole bunch of storage tanks where in the chemistry building, you can just walk down into the basement and get your dewar filled up with liquid nitrogen. And there are similar facilities in lots of other engineering and science buildings on campus. And so we routinely do experiments at much lower temperatures now. Those experiments show that the heat capacity of solids all decrease sharply at low temperature. And in fact, as the temperature begins to go closer to zero, it looks like the heat capacities themselves also want to go to zero, okay? That's at odds with this sort of the classical idea that says if this is due to vibrational motions of the atoms, again, just like in the black body case, in a classical picture, there's no reason why all possible frequencies shouldn't be allowed. Right, my atoms should be able to vibrate, take up an arbitrary amount of energy, and that would suggest that the heat capacity should stay static as we go through temperature changes. Right. So this is happening in the same time period that Planck is making the proposal about black body radiation. That leads Einstein to say, well, this heat capacity is also due to vibrational motions in solids, just like the black body radiation is. And so if the black body spectrum explanation suggests that the vibrations are restricted to certain frequencies, then that same argument ought to apply to explaining the heat capacities, right? So Einstein sets about building a model that does that. What his model does, it's a relatively simple model. It says, let's just designate a fixed frequency associated with the vibrations in a particular solid, okay? There is this so-called Einstein frequency, which is going to be found just by fitting experimental data, all right? That would depend on, say, the strength of the forces, the bonding really in the solid, right? And then the vibration of the atoms in that solid would be restricted to multiples of that frequency, right? Just like in the case of the Planck's argument for black bodies, he said there's a frequency and then it can be that frequency or 2 times that or 3 times that. Einstein makes the same argument and says there is essentially just this one parameter, the base frequency, that is going to be fit to make the data fit the experiments, all right? That Einstein frequency will be different for different materials, right? Because the heat capacity curves do look different. We'll see some in another couple minutes here. And so that gives them a floating parameter that you could do a best fit to data and then try to make sense of the frequencies that you get. So if you're going to do that, how does that get us a heat capacity? Well, again, the idea is the internal energy of the solid is stored in the lattice vibrations, right? In the first video, we talked about black bodies. One of the equations that I offered up at some point was this one here, which says this is the average internal energy, right? U is internal energy. Those brackets just denote an average quantity. The average internal energy for the quantized vibrations is just the expression on the right there, where nu is the frequency, h nu over that exponential piece, the h nu over kT, all that minus 1 on the bottom, right? And that's going to be the average energy per oscillator or per vibrational mode, right? In our crystal, our metal, or a solid, we're going to have 3 vibrational modes per atom, right? Again, corresponding with X, Y, and Z motions. We're going to take that thing and multiply it by 3 because we're going to have 3 of those modes for each atom. The n that's under here, that's the number of oscillators, right? And so we're going to say that the number of oscillators I have per mole is just 3 times Avogadro's number, right? It's 3 per atom, and I'm going to pick to have a mole of solid, and that gives me an Avogadro's number term. The n sub a is Avogadro's number, right? If you haven't gotten used to it yet, the KB term under here, that's Boltzmann's constant, and again, that one we'll be seeing throughout the course, and so you'll get very familiar with that. That gives us an expression for the internal energy, right? How is that useful? We're trying to talk about heat capacities, and remember the heat capacity is just the temperature derivative of the internal energy, all right? So the equation on top is just the one from the bottom of the previous slide that says this is my internal energy per mole up here, right? I'm going to take the derivative of that with respect to the temperature. All right, so I've got the T down here. Everything else in there, when we take that derivative, is going to be treated as a constant. And if we do that, we should get this expression down here. There is one little trick that goes on in the taking of that derivative. You'll notice that down here, I have an R that has appeared in my result. And in my top equation, I didn't have any R's. R is the gas constant there, right? And so that gets there because we've used the fact that the gas constant R is just Avogadro's number times Boltzmann's constant. Okay, so if you were to take that derivative, you would get the Avogadro's number that's up here, and you'll get a Boltzmann's constant that flips into the top when you take the derivative of that exponent in the bottom, and that's where the 3R piece comes from, okay? So this gives me an equation for the heat capacity, and it's got T's in all kinds of places there, right? So that thing definitely looks like it's going to be a function of temperature, which it is, right? It's going to vary pretty strongly with temperature, and in particular, it's going to do weird things when the temperature gets near 0, because it's got various places where it's being divided by T, right? This is the equation for the Einstein heat capacity, the Einstein model of the heat capacity, right? The only thing in there that's a parameter is that frequency nu. So if we had a set of data that were the heat capacities of an element as a function of temperature, we could find that nu, that Einstein frequency, by fitting this function to the data set, right? There's another model which your textbook measures, which is called the Debye model. The Debye model includes a range of frequencies, right? So instead of having a single frequency in there, it says there's a range of frequencies with a cap on it, and that will give a somewhat better fit to the data because it's just got more parameters in it, more things that can be adjusted, and so it gives a slightly better fit. But the Einstein model, in spite of being very simple, actually does a pretty good job, and we can see that in some graphs here, okay? So here, let's start with the graph on the left, all right? The circles on there and the X's on the diamond curve, those represent experimental results for the heat capacity of the different materials, okay? So we've got diamond, silicon, aluminum, and lead on our graph. I like to start by looking at the axes. The y-axis has the heat capacity. It says in joules per Kelvin per mole, but it doesn't have numbers on it. It does have a reference point up here where that level up there is 3R, right? So that's about 25 joules per Kelvin per mole up there. On the x-axis, we've got Kelvin temperatures, okay? So room temperature should be somewhere around here, right? And if we look at that, we can see that lead near room temperature is pretty much right on our 3R line. Aluminum is close, silicon less so, and diamond is way off from that, right? Pointed out in the beginning of this that the things that cause exceptions to that expectation of being around 3R at room temperature were light elements and things with very high melting points, right? Diamond and silicon are both of those categories, right? And aluminum is quite light. Sorry about that. And so that's why those are the outlying ones. They're in this graph mainly because it gives us a range of experimental results to look at. Okay, the blue curves through here are the Einstein expression just fit to those data, right? So a best fit to the data gives us an Einstein frequency, and you can see they all fit pretty well, right? Up here, it does look like they're all sort of coming in and they should be plateauing around that 3R value, and that does look more or less like it's happening, right? If we allow for a little bit of experimental jiggle in some of those data. These are data from the graph, the figure that's in the textbook, but the data go back to original publications, so they're kind of 19th century measurements and all that for the most part that are in those, okay? Over here on the right-hand side, we have a plot that's comparing the Einstein and Debye models. Again, the circles represent experimental data points. The Einstein curve now, you can see, is somewhat less closely fitting the data than the Debye curve. And again, that's because the Debye curve has more ability to adjust things in there. This is plotted in a slightly more peculiar way. On this axis, we've got the heat capacity divided by R, which is why the plateau up here is coming in around 3 for that one. The x-axis here is plotted as a sort of reduced variable, right? It is, says T over theta E or T over theta D for the Einstein and Debye, or the E and the D in that case, right? So if nu sub E is the Einstein frequency, then that theta sub E is defined by being h nu over kb, or I probably should have put a subscript E on the nu there to label that, okay? That thing is going to have temperature units because h nu has energy units and kb has joules per Kelvin on it, right? And so that's going to have temperature units. When I take that, I divide the actual temperature by that, I get a unitless parameter, a so-called reduced temperature would be one way of categorizing that, right? The Debye one, we would do the same expression except replace the Einstein frequency with the Debye frequency, which is the cap on the actual vibrational frequencies, okay? So we get two models that do both do a pretty good job. The Einstein model does a pretty good job. The Debye model does a little better job of explaining the data, all right? And those models work for a wide variety of things and show that quantization of the vibrational energy in solids is in fact a good explanation of why those heat capacities dive down and go to 0 as the temperature goes to 0. If you're into that sort of thing, you could take the equation from the previous slide here for the heat capacity and you could look at what would happen to that in the limit that T goes large or small, and you should get the fact that the two limits are, as the graphs show here, 3R for the high temperature limit and 0 for the low temperature limit. To sum up these first two videos, this particular slide has, again, another figure from your textbook popped in there. It says that both things, the black-body spectrum and the temperature dependence of the heat capacity, can be explained well by quantization. Right. The fact that they have the same explanation works for both is not surprising because, in fact, they're both related to the vibration of atoms in solids, right? In black-body radiation, the effect shows up at small wavelengths, right? That's the place where I get my energy dying off, because at small wavelengths or high frequencies, the separation between the energy levels is very large, and those modes can't be excited at normal temperatures, right? So this shows us over here, if this is an energy level diagram, if this arrow represents KT, right? If KT is less energy than the amount to get this vibration from its original energy up to twice that, then if this is smaller than that spacing, then not very many of these can climb up there, right? Over here, if I'm at low frequencies, this thing is frequency. This is a weird graph because it's frequency increasing going that way, right? This says at low frequencies, now the KT arrow is bigger than the spacing between my allowed energies, right? In those conditions, I'm going to have a lot of these excited, right? So those are going to be contributing in a way that's similar to their classical projection. It's the short wavelength, high frequency end of things where things are going to behave and really show that quantization, all right? In the heat capacity case, if I go to high temperatures, high temperature is going to make my KT arrow be big, right? That's going to mean that I do get things promoted up my, my ladder of possible energies. And so things behave in accordance with classical expectations, and my heat capacity approaches this 3R value, right? That's my high temperature limit. If I go to low temperatures, that says now I've shrunk this arrow, so it's again shorter than the spacing between my, my energy levels. That says that I can't get excitation of this vibration, and that means that my heat capacity is no longer going to be able to approach that 3R value, and in fact it's going to go to 0, because if T goes to 0, this arrow vanishes, and then I don't have enough energy to excite any vibrations, right? So in both cases, the place where things go and show us the quantization are the cases where my KT, my available energy, is less than the separation between the quantized energy states, right? And that's the point where quantum mechanics really shows up, is when this separation between the energy levels is large compared to the amount of energy that's available. That quantity KT that's in those little arrows there, remember KT is going to give me an energy, right? Because it's joules per Kelvin times Kelvin, right? And you can think of that as just being how much energy is just readily available thermally, right? If something is at that temperature, KT is a good ballpark guess for the order of magnitude of how much energy it might have. And so we use that quantity a lot to say this is the amount of energy that's available at a particular temperature. All right, that wraps up our quick discussion of heat capacities for now. We'll come back to those when we're in chapter 5 doing statistical mechanics. The next video, we'll talk about the photoelectric effect and ideas of applying quantization to light. Thanks.